In this lecture, we'll examine the utility of applying the student's t-test to data sets. We can use the student's t-test to describe the confidence interval for a finite data set and compare the mean values from experiments to see if they are statistically different. We cannot determine the population mean, mu, or the true standard deviation, sigma, because we typically do not have the time, funding, or fortitude to run an infinite number of measurements. What we can do is calculate the confidence interval around our sample mean, x bar. This confidence interval will tell us how likely it is to find the population mean, mu, next to the sample mean, x bar. The confidence interval is calculated as the student's t times the sample standard deviation divided by the square root of the number of measurements. The student's t is found from a table using n-1 degrees of freedom and the confidence level of interest. Let's step through an example to demonstrate this concept. Suppose we wanted to find the 50% and 90% confidence levels for the following set of measurements. The equation tells us we need to calculate the sample mean, x bar, and the sample standard deviation, s. Once we have that information, we can look up the t-value for the two levels with 4 degrees of freedom. Remember that every time we do a calculation, we lose a degree of freedom, and we have to keep track of that. With 5 measurements, how many degrees of freedom do we have? What is the value of the student's t for 4 degrees of freedom at the 50% confidence level? What is the value of the student's t for 4 degrees of freedom at the 90% confidence level? Now that we've identified our student t values, let's finish the calculation. Plugging in all of our numbers, we see that the confidence interval is plus or minus 0.13. This tells us that there is only a 50% chance that the true mean, mu, will be found in this range next to the sample mean, x bar. Now, given that our student's t is much larger at 90% than at the 50% confidence level, what do you think is going to happen to our confidence interval? The confidence interval became much wider at the 90% confidence level because we increased the probability that we'd find the population mean, mu, in this range next to the sample mean, x bar. Other than moving to a lower confidence level, how can we decrease the size of this confidence interval? If the goal is to decrease the confidence interval of our measurements, we can work on our reliability. We can do this by working on our precision, which translates into lower standard deviations, or we can make more measurements, which increases n. It's also a good idea to make measurements using 2 different methods and compare the data sets for the differences so we can detect systematic errors. Let's look at how to do that using the student t-test. We can use the student's t-test to decide if 2 data sets are statistically different. To apply the student t-test, we first have to use the f-test to determine if the standard deviations are statistically different. Then we have to pick the appropriate t calculation based on the results of the f-test. When the f-test shows that the standard deviations are not statistically different, we use t equals the absolute value of the difference between the 2 means of the data sets divided by the pooled standard deviations from the data sets and multiplied by the square root of the product of n1 and n2 divided by the sum of n1 and n2. The pooled standard deviations from the 2 data sets can be used when the f-test does not find a statistically significant difference between them. Note that we do lose 2 degrees of freedom for S pooled. If t-calc is greater than t-table at the 95% confidence interval, the results are statistically different. When the f-test shows that the standard deviations are statistically different, we use t equals the absolute value of the difference between the 2 means divided by the square root of the variance from the first data set divided by the number of measurements in the first data set plus the variance of the second data set divided by the number of measurements in the second data set. It doesn't make sense to pool the standard deviations when they're significantly different, and the degrees of freedom are calculated using a more elaborate procedure as shown here, then rounded to the nearest whole number. Regardless of how we calculate t, the rule that if tcalc is greater than t-table at the 95 confidence level still states that the results are statistically different. Let's practice applying the student t-test for the comparison of means. In this example, we're asked to determine if the average masses of nitrogen collected from two different sources is statistically different. We see here that the masses of nitrogen collected from air are all fairly tightly bunched up here, which means we'll have a lower standard deviation. The chemically generated nitrogen looks as though it has two groups of data, and they are all fairly well spread out. So we should expect the standard deviation to be much larger than that for the other nitrogen source. While looking at the data makes it seem as though the means are significantly different, we need to prove it statistically. So, what is the first step in evaluating the data set? We have to use the F-test to determine if the standard deviations from the two data sets are statistically different. To apply the F-test, we place the larger standard deviation in the numerator and square it over the square of the smaller standard deviation to make sure F is greater than or equal to 1. To help match the data, I've added subscripts to the n values, which will be important later. We get an answer limited to 2 significant digits plus 1 uncertain digit that I've subscripted here. Next, we look up F-table for 7 degrees of freedom for the standard deviation in the numerator and 6 degrees of freedom in the denominator. What does a comparison of F-calc and F-table tell us about the standard deviations? When F-calc is greater than F-table, it means that the ratio of the squares of the standard deviations has exceeded the allowable limit to be considered comparable. That leads us to our next question. Which version of tcalc do we use when the standard deviations are significantly different? When the standard deviations are significantly different, it doesn't make sense to pool their results, so we use this version of tcalc. tcalc gives us a result of 21.7, but we also have to calculate the degrees of freedom rounding to the nearest integer, as I've shown here. Now we can look up t-table for 7 degrees of freedom at the 95% confidence level. Which value do we use from the table for the 95% confidence level? All right, so 2.365 tells us what about the relationship between tcalc and t-table? We see that tcalc is greater than t-table, so what does that tell us about the means of the two data sets? Because tcalc is greater than t-table, we see that the means are significantly different.